Can you see the slides? Okay. All right, so let's get to the question. Question number 2. The Fermi energy level for a particular material at T equals 300 Kelvin is 6.25 eV. Okay, so the Fermi energy is equal to 6.25 eV at 300 K. The electrons in this material follow Fermi drag distribution function. Okay, so we're going to use the Fermi drag distribution function. So question number 1, find the probability of an energy level at 6.5 eV being occupied by an electron. Okay, so if you guys attempted the questions, dah? Easy, right? Miro, soalan pertama, okay. Very straightforward, right? Just plug in the value into the equation. Yeah, just plug in the value into the equation, just like what's shown on the slide now. So just first thing, before you do the plugging in of the figures, always write the equation. Always write the original equation. Even though you have already known the values and whatever, you know how to solve. Just write the equation first. Okay. Sebab kadang-kadang ada students, some of the students, they perhaps too excited to solve the problem, and they miss the place, or they wrote down at the wrong place or something. So it's better to have the original equation first before you start plugging in the figures. So just rewrite Fe equals to 1 over 1 plus exponential E minus EF over KT. Okay, then we know that our EF is equal to 6.25 electron volts. Okay, the T is 300 Kelvin, and the E that we want to calculate here to be able to know the probability of occupation is at 6.5 EV. Right, so just plug in all the known values, right? KT down there, when the T is equal to 300 Kelvin, the KT is usually equal to 26 milli electron volt. That's why you get this. So you get that, okay? So exponential term becomes 6.5 minus 6.25 over 0.0259. Bear in mind, this is only at 300 Kelvin. If the temperature changes, then the KT changes as well. Okay, so 0.0259, then you're gonna end up with Fe equals to 6.43 times 10 to the minus 5. Or you can also convert into percentage, and that makes it 10 to the power of minus 3%. And don't forget the unit, percent, or just without unit at all, 10 to the power of minus 5. If you want to do the calculation, say if you have a number of questions that require you to calculate Fe. So if part 1, for example, if part A you state your answer in percent, then make sure your part B is also in percent. Don't state part A in percent, part B is without percent. So you will probably end up confusing yourself later on. So when you want to do the recheck, so you might be confused with your own answers, okay? So be consistent, that's the key, be consistent. If you want to state in percent throughout, then all percent throughout. If not, then no need. Okay, done. Straightforward, right? So let's go to question number 2, part 2. This is when you have to do the ratio at higher temperature. So repeat part A, the very same thing, the very same information given, but you change the temperature to 950 K. So we increase by 650. So instead of operating at 300 Kelvin, we are now operating at 950 K. and we are assuming that EF is constant, and all the rest of the information, remain the same. So we are still required to do the calculation of FE. Okay. So what we have to do is first recalculate the KT. Okay, recalculate the KT just using the ratio there. Okay, the ratio will be given by 0.0259 times the new temperature over the original temperature. So 950 over 300. Then your KT will be a new KT. So your KT, so your KT will be a new KT then. So it's no longer at room temperature. It's no longer at 0.0259. It's now at 0.082 electron volt. And once you have got your value of KT, please double check and make sure that your KT is now higher than the previous KT. It makes sense, right? Because if you operate at a higher temperature, then your KT, your thermal energy, will be higher in the system. Okay, so in this case, now it has increased from the original version to 0.082 electron volt. Then we do the same thing, plug in all the parameters into the Fermi-Dirac distribution function. 1 over 1 plus exponential term 6.5, same thing, minus 6.25, same thing, over the new KT, and that will give you 0.0453. Okay, so if you want to convert that into percentage, so that will be equal to 4.53%. So what do you notice now if you compare part A and part B? So note the difference of your FE. Okay, so your FE has now increased from 6.43 times 10 to the 3 percentage to 4.53. So that's like a couple of orders of magnitude. Okay, 10 to the minus 3 to 10 to the 0. So that's like 3 orders of magnitude higher, just by increasing the temperature from 300K to 950K. Okay, so your FE is now higher in comparison to the previous case. Okay, so that's quite straightforward. So the tricky part is probably the KT conversion, but so it's known already now. You just have to do the ratio, get your new KT, make sure your new KT is higher than your previous KT because the temperature is higher. So whatever you get in your answers, make sure the answers make sense. Okay, for example, in this case, if your answer for part B, is lower than part A, for example, so does it make sense? If your part B is lower than part A, does it make sense? It doesn't make sense, right? Because your temperature is higher, how come your KT is lower? When the KT is proportional to your temperature, KT is proportional to temperature, right? So it cannot be lower. So if it's lower, then that means your, I don't know, calculation or conversion is wrong somewhere. So better recheck. So that's why the moment you got your answers, please make sure that your answers make sense. Okay, you can explain. You should be able to explain the answers. Why is it higher? Why is it no change? And why is it lower? Stuff like that. So try to relate back to the thermal excitation and energy supplied, transition from valence band to conduction band, so on and so forth. Okay, make sure your unit is uniform. Okay, macam Amiro, make sure your unit is uniform. You can use either one in Boltzmann constant, but in this case, you need to use according to the correct dimension. Okay, you can tell that by looking at your Boltzmann constant, what's the unit there, and then try to relate to the current unit being discussed. So if the unit being discussed is not the same as your unit that you want to use, then of course it's not in the right dimension. Okay, use in the same dimension. Then you're going to end up with the right answer, or else you're going to end up with the wrong answer, wrong numbers. Okay, number 3. Now we are asked to calculate the temperature instead. So the previous one, the temperatures were given. Now the temperature is requested. So calculate the temperature at which. So you have to be able to translate this into mathematical equation, at which there is a 1% probability. So 1% probability. So equals to 0.01. that a state 0.3 EV below EF. Okay, so in the last, I think last 2-3 years ago, last 2-3 years ago, I used the very same question in final exam, exactly the same question as what was discussed in the class, and still some students got it wrong. Because where did they get wrong? They got it wrong when they wanted to translate the information in the statement here in the story to the equation, into the equation. So that's where they miss. So the moment they translated the information wrongly, then they used the wrong information in the equation, calculated wrongly, got the wrong answer. Okay, as simple as that. So it stems from translating the statement, the mathematical statement into equation. So look at this: 1% probability that a state below. So below EF, so that means the energy state, the E here is 0.3 EV below EF. So later on, if you plug it into the equation, E minus EF, so that'll be obviously minus 0.3, right? E minus EF minus 0.3 EV, because it stays below EF. So if it's above EF, then E minus EF is positive 0.3. So look at that final statement. Will be empty of an electron, right? So are we using Fe in this case? Are we using Fe or 1 minus Fe? Empty of an electron. A hole is a vacancy of electron, right? So it's the reverse. Okay, 1 minus, right? So it's the reverse. So make sure you translate everything correctly. So let's go to the example, to the final calculation then. So the equation becomes Fe is Fe 0.1% empty of n electrons. So that means your calculation will be 1 minus 1 or 0.001 will be equal to 0.99. Okay, 1 minus, and plug in the very same equation, 1 over 1 plus E minus EF is equal to minus 0.3 because your energy state is now below your Fermi level, over KT, right? KT, just leave it there first. You can replace your Boltzmann constant already, but the temperature is not known. Then rearrange the equation into the below lines here, below rows here, and then convert, and then you're gonna be left with T equals to 756 Kelvin. Okay, so we do the natural log conversion due to the exponential term being the opposite side. So you're going to end up with T equals to 756 Kelvin. Okay, so this is among the what we call the question. This is among the question that's usually being tested in the final exam. So just remember, for this batch, for this semester, as of now, we're still sticking to 50-50, final exam 50 and your coursework 50. As of now, we don't know yet for sure, but if the moment we receive the latest directive from USM top management, from the NCAA, then we'll see how do we actually do our final, whether it's going to be still 50-50 or converted into 100% coursework, just like last 2 semesters. Okay, so usually in my course, when we convert it into 100% coursework, then it's going to be open book test for test 1 and test 2. Open book. Have you ever experienced any open book test before in your previous semesters? Anyone? Tak pernah. Any courses? Yes. Faris pernah. Okay, Cornelia pernah. Open book test, is it easier or harder than the typical test? Juaria said tough. What's the tough part, Juaria? Would you like to share a bit? What is tough in open book test? You can open the book, right? You can Google search and everything. So what's the tough part? Okay, you can find notes from, you cannot find from the notes, thinking more, okay. What does it mean by open book? So did you get to do Google search as well in your previous open book? Or strictly to certain notes, or how? Is it like any, you can, okay. Okay, so you can open resources, but you cannot find anything. Okay, open book is like open, right? You can, the information can be anywhere and it's not restricted. Of course, it's not restricted to the nodes because or else why open, right? So in my course, in my two courses, 386 and 487, during pandemic, both were done with open book tests, test one and test two. It requires some good fundamental in your learning. Then the moment your fundamentals are good, you can search and find anything. Because if you go online, you will see thousands of different information, right? So then the challenges will be to filter what is the most important one and what is the most accurate one for the context of the questions being tested. But we'll get to that later on before our test one. Probably sometime week 6, I think. If I'm not mistaken, week 6. We'll get to that. Okay, so done. Let's continue with our next topic. So the calculation is clear, right? It's quite straightforward. You can do more calculations in Niemann's textbook. There are a range of different ways the question can test you. But this is only the basic one. So let me get to the intrinsic and extrinsic semiconductor. Hold on, yeah. Intrinsic and extrinsic. Okay. Okay, can see the slides? Okay, good. So now we are moving into intrinsic and extrinsic semiconductors. Okay, so it's getting a little bit more complex. So intrinsic in in a simple translation is called pure semiconductor, where you don't do any doping. So you don't introduce any foreign atoms into the lattice at all. So what you get is basically the intrinsic properties or the original properties of the semiconductor material. On the other hand, extrinsic is the doped semiconductor. So either you make it P, you make it N at any level. The moment you include some foreign atoms into the lattice, the semiconductor will become extrinsic. It's no longer intrinsic. Okay. So let's recap a few things before we continue as usual, so that you have the right understanding from our previous topic. What is Fermi-Dirac distribution function? Anyone? How would you define Fermi-Dirac distribution function? What's the easiest way to define this?
F E equal
Yep.
to
Is it?
F E equal to 1 over sorry, forgot already. Apa dia punya
1 over 1 plus
1
exponential.
plus exponential E minus EF over KT.
Yeah, right. So that's correct. So what you have to do first is just write down the equation, define all the parameters in the equation. And then if you get to, if you're asked to answer this question, also include the step function profile at T0 Kelvin, and then T equals T1, T equals T2, what happens to the distribution of the electron in the conduction band and hole in the valence band, the area under the curve and stuff like that, right? So this question alone can give you 20 marks. So this is very simple one, but then it may carry 20 marks. So in my previous experience with previous batches, some students do not have capability to gauge how much need to be answered. So for example, if the question asks you something and then it states at the end 30 marks. So some students I saw just write down like 2-3 points and then they think that they can get 30 marks. Of course cannot, right? So you should be able to have the capability to gauge how much is asked. If, for example, if that question states 5 marks, then of course it's just like listing stuff. If like 20 marks or 30 marks, then of course you have to do some explanation. What does it mean? So what trend do you see? Even though the question is very simple. So you should be able to have some capability to translate, to understand what is required from the question. Okay. So if you see 20 or above, then that means you need to do some explanation quite intensively, right? Not just listing. If it's like 5 marks, then probably just bullet point 1, 2, 3, done. Maybe 5 marks already. So you should be able to understand what's required. Okay, so don't just give the Fermi direct distribution function and done. Of course, that would be 30 marks, right? It's not fair if that alone gives you 30 marks. Okay, good. Second one, what is density of states? Anyone? Apa density of states? How would you define that? Arisha, before I get to Amirul. Arisha, what is the density of states? Let me hear some of you yang saya tak jarang nampak nama kat sini. Kavina said number of allowed energy states per centimeter cube per energy level. Yes, okay. So you can define that as oh, Rosa I, okay, right, tak apa. Arisha, yes, okay. Connection slow. Okay then, no problem. Number of allowed energy states per centimeter cube per energy interval. Okay, so that's density of states. Okay, why is it important? Why is density of states important? Why do you have to know density of states? How would you answer that? Siapa lagi ni? Saya jarang dengar nama. Yeah. Anyone would like to answer? Hasnain. Hasnain? Kalau duduk dalam kelas senang sikit, I can just go to you and ask. Sekarang susah sikit. But anyway, let's discuss. Let's, if you discuss, you learn more. So Hasnain, what do you think? We want to, we want to know the number of electrons, etc. Yep. We want to know how much electrons can occupy the states, right? So that's why the definition of density of states is, if you go back to Kavina's answer, number of allowed energy states per centimeter cube per energy level, per energy interval, if like. So that's the number of allowed. So just like my analogy last time, so you want to know how big is the room so that you can plan how many can go in, right? So the size of the room is the number of allowed energy states or density of states, and how many of you can occupy the room then will be the density of electrons, density of free electrons. Okay, so you just remember that. Then you should be able to translate what the actual meaning is. Don't translate how what I call the size of the room pula dalam dia punya jawapan. Of course not. I'm just giving you analogy for you to understand easier. That's all. Right? So density of state is the size of the room that can be occupied. For example, if you rent an apartment, how many can go in? Say 7 people, for example, and then the limit will be 7 people, right? So that means 7 electrons can be excited, for example, in that case. Okay, what is probability of occupation? Number 3. Anyone? Sakina, not Sakina. Before we move on to intrinsic and extrinsic, so what is probability of occupation? How would you define? Look at the keywords there. Probability of occupation. Same thing, right? Same thing like the first one. Okay? Just like the first one, it's the very same equation. Probability of occupying the states. So which is given by Fermi direct distribution function, Fe, blah, blah, blah. Okay, so how do we then calculate density of free electrons or free hole, for example? What is the simplest way to say that? Before you go to the long one, what's the simplest way to answer this? What the simplest equation can you write? Yeah, the formula which states that, what does it say? Has it the formula? Ne equals to
And E equals to Fe
times
times N NE NV
okay.
uh,
Okay, kalau electron, so density
NCE
of states.
NCE sorry.
Yeah, okay. Ne equals to NCE, which is the density of states in the conduction band, times FEN, property
FE.
of occupation, right? So that is for electron. Yeah, multiply DOS with occupation probability, right? So don't be confused with the one on the hole, because the hole will be 1 minus, PE equals to NVE times 1 minus FE, right? So NVE is for conduction density of states in the valence band times probability of not occupation, the reverse probability of electron occupying that state, or 1 minus FE. Okay, so done, clear. If you're clear about all these questions, then you're clear about the previous topic. That's all. So this is the gist, the essence of the previous topic. If you're clear about this, then the elaboration of each will become easier. Okay, right. So now we are in the next topic, intrinsic and extrinsic. So we're going to cover a couple of items, maybe the first few parts in the remaining time. Intrinsic carrier concentration, which belongs to intrinsic semiconductor, then extrinsic semiconductor, doped silicon, which is technically extrinsic as well. Fermi level in doped semiconductor. So we have discussed about the Fermi level in our intrinsic, which is in the middle of the band gap, or pretty much equals to Eg over 2. But we're going to see how the Fermi level changes in our doped semiconductor. Either it's N-type or P-type. Okay. Conservation of charge. Okay, when you dope, what happens to the ionized dopants and stuff? Then degenerate semiconductors, which is referring to when you dope your semiconductors too heavily, either p-type or n-type. If you dope at above certain level, and you will see the EF is too close to the band edge, either conduction band or valence band, and at that point, you will know that the semiconductor now becomes a degenerate semiconductor. It's no longer a normal semiconductor. So we're also going to learn about compensated semiconductor. So what does it mean by compensated? And then we're going to see how does a Fermi level varies with doping and temperature. So we're going to see how we can alter or we can modulate the level of EF in our semiconductor in order to get certain properties of your semiconductor layer or device. All right, intrinsic semiconductor is a pure semiconductor. So when we say intrinsic, it's pure, nothing else. So pure means there's nothing inside the lattice but the original atoms. Okay, so if you're talking about intrinsic silicon, then just silicon, no phosphorus, no gallium, no arsenic, no nothing, just silicon, pure. Okay, so original lattice, so that's called intrinsic semiconductor. All right, an intrinsic semiconductor is a pure semiconductor that is no dopant. Number of charge carriers is determined by properties of the material itself. So it depends on the original properties of the material instead of the number of impurities, instead of the amount of impurities. Impurities do not affect the intrinsic semiconductor because they are not there in the first place. On the other hand, we're going to see later on when we talk about extrinsic semiconductor, the amount of impurities, in this case, if you're talking about desired impurities like dopants or undesired impurities like ions and others which are not desired to be in lattice in the first place, will affect the properties of the semiconductor. Okay, in intrinsic semiconductor, number of excited electron and holes are equal. Okay, Okay, bear this in mind. In intrinsic, number of excited electrons and holes are equal. Why number of holes and electrons? Why the number of holes, excited holes and electrons are equal? Why do you think they are equal? Nurul Nabila. Why the excited electrons and holes has to be equal? Any ideas? So ayat yang saya garis tu, the number of excited electrons and holes are equal. Why can they be not equal? What do you think? Because they are stable. Okay, Joanna said because they are stable. All right. Okay, any other answers? Why for every excitation you need to have the same number of electron and holes in intrinsic? Because it is pure. Okay, go. It's pure. So if it's pure, then what happens when you do excitation? What do you get? So let's go back to our previous fundamental knowledge. When you get excitation, so excitation here means you get your electron into the conduction band, right? What do you also get at the same time? Can you get, Amiro said a hole. Can you, during an excitation, can you get a free electron in the conduction band without getting a new hole? Can or not? Why cannot, Amiro? They come in a pair, right? They come in a pair. So we even call them electron. Alamak, sorry. When I write down the screen, it moves. They are always called electron hole pairs. They come in pair. So the moment you get a new electron, yes, the moment you get a new electron, you will also get a new hole. What is hole? Vacancy of electron, right? So it's like husband and wife. So they come in pair. If you go to Kenduri or whatever, they come together, right? Unless seorang is on fever or something. Usually they come together. Apa tu, Wonder Vision? So, well, bottom line, they are in pair. Okay, they are in pair. So the moment you get a new excited electron in the conduction band, you will also get a new hole. So that's why the number of electrons and holes will be equal in intrinsic semiconductor the moment you get excitation, right? So when you get when they come together in electron hole pair, when you break the pair, you will always get electron and hole. One into the conduction band, one remains in the valence band. Okay, so that's why the moment you get N naught, which is density of electron in intrinsic, or if you like in thermal equilibrium, will always be equal to density of hole at the same time. Okay, because they come together, the origin is together, right? Then you break them so that you can do excitation. So you got one in the conduction band, and you got another one left in the valence band. So that's a very fundamental principle that you have to understand first before we start talking about extrinsic. Because extrinsic, you're gonna add something of one polarity. So you can either add more holes or more electrons to the stable system that originally has equal number of hole and electrons. But later on, if you go n-type, if this is electron, this hole, equal number in original system, in intrinsic, if you go n-type, you're going to add more electrons. More this, you're going to have more electrons. But this one, no. Okay? All right, so intrinsic carrier concentration is a very strong function of temperature. Why? Because we've discussed before that the carrier concentration is determined by your thermal excitation, right? So we have also discussed in your example number 2 just now, when you increase your temperature from 300K to like 600K or 950K, you have also seen that your Fe is higher, right? So your Fe is higher means you can find more electrons at that particular energy state. So the probability of finding that electron. So when you say that your probability is higher, that means you have more electrons that can be found by the Fermi-Dirac distribution function. So therefore, thermal excitation at higher energy will give you more and more excitation, and more intrinsic concentration will be produced at higher temperature. Okay, so at 300 Kelvin, if you talk about intrinsic carrier in silicon, the Ni is equal to 1.5 times 10 to the 10 per centimeter cube, if you look at silicon. Okay, so you may also encounter that this Ni equals to 1 times 10 to the 10 in some references. Okay, so you can either, for me, if you want to do your calculation later on, for Ni, for silicon, it's easier for you to use 1 times 10 to the 10, because if you want to do division or whatever, it's easier to divide by 1, right, instead of 1.5. So your math operation will become a lot easier. So you can use 1 times 10 to the 10 instead of 1.5. It's easier to do. You don't even have to press calculator. Okay, because you divide by 1, so it's the very same number, and you just have to look at the 10 to the power of whatever to do the operation. Okay, so you can use 1 times 10 to the 10, but if you use 1.5 times 10 to the 10, you are not wrong as well. So you can use either one, but for the sake of calculation, you can use 1.0. Okay, and even though you use either one, you will notice that later on the difference in the answer will not be so significant. Not significant. You can see the last statement there. Okay. So if I were you, I would use 1 times 10 to the 10 because it's not wrong anyway. So for an electron hole pair to be created, okay, for you to create electron hole pair, a bond must be broken. So that's the key. So they come in pair, right? Electron hole pair. To be able to get a free electron, you need to break the bond. You need to break the bond so that this guy is free going up and this guy is free remaining in the VB. This guy is going to CB and this guy stays in the VB, right? So therefore you have to break a bond first. And this requires energy, like thermal excitation, like this now. An electron in the VB must gain enough energy to jump to the CB and leave behind a hole. So the moment you have electron in the conduction band, you will also create a hole in the valence band, right? So since Ni represents intrinsic carrier concentration, it also represents the number of bonds being broken in intrinsic. So intrinsic carrier concentration also represents number of bonds being broken, because to be able to get that free electron hole pairs, or free electrons in the conduction band, or free holes in the valence band, you need to break a bond. And the number of bonds will be corresponding to the number of intrinsic carrier concentration that you want to produce. Okay, they are proportional to each other. Okay, why more carriers at higher temperatures? We have discussed this one before, thermal excitation, right? Thermal excitation. You can also say this in the form of KT. You have seen in the calculation later on, just now, when you change your KT from 0.0259 to 0.082 electron volt, when you increase your temperature from 300 Kelvin to 950. So it's due to additional energy that can break the original bond. Therefore, you'll get more free electrons, right? Or more electron hole pairs created. So more electrons from VB gain enough energy from the KT, from the thermal energy, to jump across the band gap. Okay. So you can see this in the graph here on the left. Intrinsic carrier is on the y-axis, and the temperature, the reciprocal of temperature, not temperature, reciprocal of temperature, because 1000 divided by T. So you will see the inverse of temperature. Okay. So maksudnya dalam graph ni, if you increase the temperature, are you going to the right or to the left? On the x-axis, okay, 1000 over T. If you increase your temperature of your silicon, are you going to the right or to the left? To the left, right? Okay, because it's the inverse of temperature. So if you increase your temperature, your denominator will become bigger, so therefore 1000 over the bigger denominator will become smaller, so it's the inverse. So that means if you increase your temperature, you're actually going to the left, right? To the left. So you can also represent this, if you like, by, well, you can plot something like this to make more sense. Ni, the very same thing on the y, and you can say O against t, and you will get something like that, right? And this chart is about inverse of t, so that's why you get something like that for 1000 over t, and this one is t, right? If you're plotting 1000 over t, then you're gonna get inverse relationship. But if you plot against t, you're gonna get a proportional relationship. So in this case, if you go left pergi kiri, that means higher temperature. So therefore, your intrinsic carrier increases accordingly, okay, in silicon. For example, if you're operating here at 3.0, so your carrier is like 10 to the 11, close to the intrinsic carrier concentration, which is 10 to the 10 just now. If you increase to say 1.5, then you're going to end up with middle of 1016. Okay, so you're moving from 1011 to 1016 by increasing the inverse temperature from here to there. Okay, quite straightforward, right? So you can either represent by this or the second graph now. Extrinsic. Okay, extrinsic. What is this? What is this drink? Cincau, lengkong. We're going to be in Ramadan very soon, right? Like 2 weeks time, less than 2 weeks time. So extrinsic semiconductor is no longer pure. Nasib baik tak puasa lagi ya. If it's a fasting day, then maybe you'll be thirsty already by now. Right? Extrinsic is no longer pure. Intrinsic is, right, mineral water, if you like. Then extrinsic is something else. Ais ke dahaga pula tiba-tiba. You put something in there, right? Like cincau, lengkong. Okay, whatever. Let's continue with another few minutes of extrinsic. Okay, extrinsic semiconductor is a semiconductor into which an impurity or dopant has been introduced. Sorry. So you now have impurities or dopants. As we talk about our previous, I think our first or second lecture, impurities can be desired impurities and undesired impurities, right? So undesired can be like oxygen or carbon or metals, which are not supposed to be in the lattice, but they are there somehow by accident or by certain process or something, right? We're going to learn later on. On the other hand, we also have desired impurities, which are dopants, okay, which are dopants, which will be introduced in order to alter the conductivity of your semiconductor, just like what we discussed in our first lecture. So it's been introduced, giving it different electrical properties than intrinsic. So you want to alter the electrical properties of your semiconductor. So for impure or extrinsic, you can say impure or extrinsic. In this case, N is no longer equals to P. So when we talk about intrinsic just now, we know that Ni is equal to N naught is equal to P naught, right? So for every bond broken, you're going to have the very same amount of electrons and holes being created. On the other hand, in extrinsic, N is no longer equal to P because, why? Why is it so? You are introducing one sort of dopant into the lattice in order to get it more N-type or more P-type. More N-type means more electrons, more P-type means more holes. So in that case, in those cases, more electrons and more holes, certainly the number of N and P is no longer equal, right? Because you are skewed already to certain conductivity, to certain polarity, either it's more positive or more negative. In fact, small amount of impurities can radically change the electrical properties of the semiconductor. So it doesn't have to be a lot. It can just be a little amount of impurities that can alter the conductivity. For example, if you can recap, group 5, if talking about silicon as your host, lattice. So if you're incorporating group 5, you are introducing 5 valence electrons, right? Group 5 or group 15, 5 valence electrons, and silicon has 4 valence electrons, so therefore we're going to have 1 free electron for every bond. So this free electron is going to wander around the lattice for conduction, right? So the fifth one is easily ionized. Hold on, yeah. So it requires only like 0.02 amount of energy in order to be ionized, ionization. So we've discussed last time that I think Hazik did ask about do we get everything contributing to the electrical conductivity, right? It's from you, was it? You said someone said about do we get every single atom to contribute to the conductivity of the semiconductor, or do we get everything ionized, stuff like that? And we started discussing about ionization efficiency and stuff like that. So in this case, if you put a dopant like phosphorus, it only requires 0.02, which is very small amount of energy for it to be ionized in the lattice in order to contribute to the conduction. Okay, if you don't have this much of energy, then that means your phosphorus will just stay there idling in the lattice, not contributing to the conduction. So you won't get your objective achieved because it's not ionized anyway. You just put it inside the lattice, but it's not doing anything. So it's not contributing anything. But your goal is to alter the conductivity, right? To make it more n-type. But you're not getting it because it's not ionized. But in this case, it's easily ionized. So you won't be able to have a problem with phosphorus. Okay. On the other hand, if you want to make your silicon more p-type, more positively charged, so you need to have add dopants from group 3, like boron, for example, which has 3 valence electrons. And remember, silicon has 4. So now we have one short, or we have a short of 1 electron, right? A short of 1 electron. So 4th electron is easily accepted from the lattice, leaving behind a positively charged hole. So that's how you get a hole in the lattice. Again, the required energy is very small, so that's just 0.02 eV. So that's why most of the time we get most of the dopants ionized in the lattice to contribute to p and n-type conduction, right? So I'll just stop here for the extrinsic. Tomorrow is what? Tomorrow's Friday, right? So no class. Okay, no class tomorrow. I'll see you again next Monday. So can you follow so far with intrinsic and extrinsic semiconductor? Is it okay? Yep, good. Intrinsic is pure, extrinsic is impure. Intrinsic is undoped, extrinsic is doped at whatever level. P-type, N-type, 1014, 1016, 1019. As long as you put something into the lattice, it's already impure or extrinsic. Okay? Okay then, so I'll see you. No problem, Mushfiq, no worries. So I'll see you next Monday then, okay? Bye-bye, take care. Assalamualaikum. Stay safe.
Thank you, Doctor.
No problem. Bye-bye.